Assalamu alaikum dear students, I hope you all are fine and in the best conditions of your health. So in today's lecture we shall discuss about the dehydrogenation reactions that involve formation of carbon-carbon double bond. So the key concepts of this lecture will be the redox reaction. So we will have some overview about what do we mean by the redox reactions. Then we will consider about the oxidation reactions and their different types, and followed by we shall discuss about how we can carry out the dehydrogenation of alkanes. So what do we mean by redox reactions, right? So redox reaction or the redox is actually a combination of two words, that's oxidation and reduction, right? So these reactions go in parallel to each other. What we mean by that these reactions go in parallel with each other, that it means that when we oxidize something, there is something in the reaction that is also getting reduced. So we cannot oxidize a chemical species without simultaneously reducing the other species as well, right? So as a result, the organic reactions, the organic oxidation reactions requires something that has to be reduced as well. Similarly, when you are carrying out reduction of some organic compound, it means you must have something which has to be oxidized, right? So normally the reagents which we use in the organic reactions are the inorganic reagents. It means that when we are oxidizing an organic compound, it means that inorganic reagent must be reduced. And when we are carrying out the reduction of an organic compound, it means that that inorganic reagent which we are using must be oxidized. Right? So overall, the oxidation and reduction reactions, they involve the transfer of electrons from one species to the other. The species which is oxidized is losing electrons, and the species which is reduced is gaining the electrons which are lost by the oxidized species, right? And the reagent which carries out the oxidation is called the oxidant, or the oxidizing agent, right? So oxidizing agent does what? Oxidizing agent oxidizes the organic compound and will get itself reduced. Similarly, the reducing agent is any agent that reduces the organic compound and it's itself oxidized. So sometimes it becomes confusing how the electrons are flowing. So if you have trouble remembering the way of electrons flow in oxidation and reduction reactions, so you can have this as a hint. So the word oxidation starts with O, and this O is also the second letter of positive, right? So it means that anything which is getting oxidized will get positive charge, right? So things get positive when they are oxidized. Similarly, the second letter of the reduction is E, and E is also the second letter of negative. It means if something is becoming reduced, it will become negative. Or you can say if things are getting negative, it means they are reduced, right? So just by checking the charge, you can see if a thing is oxidized or if a thing is reduced. So if a thing is getting, if a species is getting a positive charge, it means that it is becoming oxidized, and if a species is getting a negative charge, it means that species is becoming reduced. Now let's see about the organic redox reactions, right? So we say that in redox reactions, the electrons are flowing from one species to another. So species which is losing electron is actually being oxidized, and the species which is gaining the electron is actually being reduced. But by just seeing the organic reactions, we cannot say that which of these is gaining electron and which of these is losing electron, right? Just for example, let's see this interconversion. So here we are converting this secondary alcohol to a ketone, right? So we say that ketone is more oxidized form, but we cannot say how the electrons are flowing from each other because there is no positive charge or there is no negative charge, right? So we just by seeing the organic reactions, we cannot tell, okay, so where is electron flowing from, right? But the electron transfer becomes visible when we look into the inorganic reagent, because in the organic reactions we are making use of the inorganic reagents. So when we are interested to see where the electron is flowing, we don't look at the organic reaction. Instead, we look at the inorganic reagents which are used in the reaction. For example, consider the same reaction. So here we have a secondary alcohol and it's being oxidized to a ketone, so we don't know how the electrons are flowing. But if we just look at the inorganic reagent, so in this reaction we are using the chromium 6 as the reagent. So you say that the oxidation state of chromium 6 is changing to the chromium 3. So it was previously positive 6, now it is becoming positive 3, right? So positive number is decreasing. So decrease in positive number means the chromium is becoming more negative, and when something is becoming more negative, that means it is becoming reduced. So the chromium is being reduced to chromium 3. So if chromium is reduced, it means our alcohol is being oxidized, right? So this is the way we say if organic compound is oxidized or reduced, that we don't see the organic reagent. Instead we use the inorganic reagent to see the transfer of charges or the transfer of electrons. Another way, if we want to see if the organic compound is more oxidized or more reduced, is seen to the table, right? So this table is giving you the oxidation number of the carbon, right? So in this table you can see that these are the function groups that have 0 oxidation number, right? So this is an alkene with the triple bond, and there we have some alcohols, right? And so these are having 0 oxidation number, right? So this is a secondary alcohol, you can see here, and here we have an alkyne. So this alkyne is disubstituted, right? So alkynes and these alcohols which are secondary, they are having 0 oxidation number. Then we have this aldehyde. So aldehyde plus 1 oxidation state, right? So it means this aldehyde is more oxidized compared to this alcohol because it has positive charge, right? More positive, more oxidized. So here we have a ketone. So ketone has positive 2 oxidation state. It means that oxidation number of ketone is higher than aldehyde. And here we have carboxylic acids or derivatives of carboxylic acid. So they have oxidation number of positive 3, right? So more positive, more oxidized. On the other side we have this alkene, and we have primary alcohol, and we have alkyl halide. So these can be any electronegative element, right? So all of these have -1 oxidation state. It means that these alkenes, these alcohol, primary alcohol, and the alkyl halides, primary alkyl halides, all of these are more reduced as compared to the alkyne and the alcohol. Then we have this alkane, right? So this alkane that's having more than 1 carbon atom, that has -2 oxidation state, and when we have this R group in which the number of carbon is lesser, it has -3 oxidation state, right? So more negative, more reduced, more positive, more oxidized, and this is the 0 oxidation state. That means that's the standard value, that's the central value for this thing. So when we have to oxidize these species, we have to reduce the oxidation state, becoming more positive, and during the reduction of these species, the oxidation number decreases or becoming more negative. So from the table it can be easily seen that the oxidation number becomes more positive, the carbon becomes oxidized, the oxidation state becomes less positive or more negative, the carbon becomes reduced, right? So you don't need to memorize these oxidation numbers, just learn the relative locations, right? So by just seeing the relative locations, we know, okay, so we have an alkane, so that's more negative. We don't need to remember the number, we just know that this alkane, that's more negative, that's more reduced. Then we have alkene, so alkene is less reduced as compared to this alkane. Then we have alkynes, so alkynes are more oxidized as compared to this alkene, right? So just remember the locations, you don't need to remember the number. So in organic chemistry it's not important to remember that this oxidation state is -1 for this function group, or the function group has 0 oxidation state. You don't need to memorize the oxidation numbers, just memorize the relative location of the compounds in that table, right? So another way in which we can learn about the oxidation level of an organic compound is by comparing the relative number of hydrogens attached to carbon, right? So suppose that we have these different groups. We have methane, we have an alcohol, and an aldehyde, and then carboxylic acid and carbon dioxide. So just by saying that this methane, it has maximum number of hydrogens attached. So with maximum number of hydrogen attached, that is most reduced. So as the number of hydrogens get on decreasing, the oxidation level is increasing, right? So this is ketone, so this has maximum, this is methane that has maximum number of 4 hydrogens, right? So there we have an alcohol. So in case of alcohol, we have got a oxygen, right? So here we say that directly bonded hydrogen number has reduced. So overall the number of hydrogen is the same, but directly bonded hydrogen has reduced. So it has 3 directly bonded hydrogens, so it is more oxidized as compared to methane. Then in case of this aldehyde, so now we have 2 hydrogens here. So this carbon has only 2 hydrogens, so that's more oxidized as compared to alcohol. In case of carboxylic acid, we have 2 hydrogens, but the number of hydrogen directly attached with this carbon is only 1, so this is more oxidized. Then we have carbon dioxide. So carbon dioxide has no hydrogen attached to the carbon, so this is the most oxidized form, right? So by just seeing the number of hydrogens directly attached with the carbon, we can predict about the relative oxidation number of an organic compound. Similarly, if you have an organic compound with more than 2 carbons, then we can similarly predict the oxidation number as well. So just you have to see the number of hydrogens, right? So in this case, this 2 carbon ethane, that's the most reduced form because it has maximum number of hydrogens. Then we have an alcohol and an alkene. So both of these are having same oxidation number. Alright, so both of these will have same oxidation number. In case of this aldehyde and epoxide, so both of these are also having same oxidation number. So just see that in moving from this position to this side, so as the number of hydrogens directly bonded to this carbon are decreasing, the oxidation number is increasing, right? So this is most reduced. Then alcohol or alkene have same oxidation number and it's more oxidized than this ethane. And we have aldehyde or an epoxide, so both of these have same oxidation number, right? And they are more oxidized as compared to the alcohol and alkene. And here we have this carboxylic acid. This carboxylic acid is the most oxidized form of 2 carbon system, right? So if you see about in this series, you see that this ethanol and this ethene, they are having the same oxidation number. And if you remember the just basic reactions of alcohols and alkenes, you know that alcohols can be converted into alkene and alkene can be converted into alcohol by simple addition or elimination of water, right? And since both of these have same oxidation level, it means there is no change in oxidation state of the alcohol or alkene when these are interconverted into each other, right? So when alcohol is converted to alkene, the oxidation number will remain the same, and when this alkene is converted into alcohol, the oxidation number will not change, it will remain the same. Now when we talk about the organic oxidation reactions, right, the oxidation of carbon involves one or more of the following, right? So number one, an organic compound in which there is an increase in multiple bond order of the carbon, that is said to be oxidized. For example, if you have a carbon-carbon single bond and it is reduced and it is being converted into carbon-carbon double bond or a carbon-carbon triple bond, we say that multiple bond order has increased, right? So if there is increase in multiple bond order of the carbon, then in that case we say the organic compound has oxidized. Similarly, if there is increase in oxygen or if there is an addition of oxygen to carbon, so this is also an example of oxidation reaction of the organic compound. Or there may be replacement of hydrogen on carbon by oxygen, right? So it's important that you have to replace the hydrogen directly attached to carbon, right? So if there is replacement directly attached to carbon by oxygen, then in that case the reaction will be considered as organic reaction as well. So just for example, here we say, so in this case, so overall the number of hydrogens is the same, but we have directly attached an oxygen to the carbon, so we have replaced one hydrogen with oxygen. This is oxidation. Similarly, compare this ethane with this ethene. So here we have created a double bond, so the multiple bond order has increased. So this is again an oxidation reaction, right? So in case if we introduce an oxygen into the system, like epoxide or aldehyde or alcohol, that's also an example of the oxidation reaction, right? So by combining all of these three parameters, that increase in multiple bond order, right? So increase in multiple bond order occurs by elimination of hydrogen, or the addition of oxygen to carbon, or replacement of hydrogen directly attached on carbon by oxygen. So if you combine all these criterion, then definition of oxidation for organic compounds will become: the oxidation of organic compound involves either a gain in oxygen or a loss of hydrogen, right? So in all of these reactions of the organic compound, we'll see if something is gaining oxygen or something is losing hydrogen, right? So either gaining of hydrogen or loss of hydrogen, gaining in oxygen or loss of hydrogen will be considered as the oxidation reaction. Now let's see about the dehydrogenation reactions. D means removal. Hydrogenation is a term that's including this hydrogen, right? The D means removal, and hydrogenation means D of hydrogen, removal of hydrogen. So those reactions that will involve the dehydrogenation means those reactions will involve loss of hydrogen. So dehydrogenation is actually a type of oxidation reaction, right? So dehydrogenation reactions involve removal of hydrogen from an organic compound. It's an important reaction because by this reaction we can convert the alkanes, which are inert and less valued because they are not reactive, into more reactive alkenes, right? So by dehydrogenation reaction, the dehydrogenation reaction is very important because by this reaction we can convert the alkanes into alkenes, right? So the alkanes are less reactive, they don't react at all, but alkenes are more reactive. So by that method we can convert the alkenes into alkenes, which are more reactive and are more useful. So these processes are normally highly endothermic, means you have to give high temperatures of 500 or above, and by this method of dehydrogenation we can convert the saturated fats into unsaturated fats, and sometimes we can also make use of enzymes, right? So the enzymes which carry out the dehydrogenation reactions are known as the dehydrogenases enzymes. So sometimes it becomes confusing between the terms of hydrogenation, dehydrogenation, hydration and dehydration. So whenever you have just confusion, just remember that whenever there is a hydrogen, it means the reaction will involve addition or elimination of hydrogen. So in hydrogenation, you can identify this as hydrogen. So that reaction involves addition of hydrogen. And dehydrogenation, you can see the hydrogen here, so it means the removal of hydrogen. Well, when there is hydration means there is addition of water, and dehydration means that will removal of water, right? So in case you have any confusion about the dehydrogenation reactions and the dehydration, just identify if there is a hydrogen inside the word, means you are dealing with addition or elimination of hydrogen, and if the word has hydra inside or hydrate inside, that means you are dealing with addition or elimination of water, right? So addition or elimination of water is not a type of redox reactions. So this hydration and dehydration, that is not a type of the redox reaction. So we don't discuss these reactions in the redox reaction, right? So there are different types of dehydrogenation reactions, right? So these involve aromatization. So when we have a 6-membered ring and we carry out the elimination of hydrogens from the 6-membered ring, we get a benzene ring, right? So that's an example of aromatization. Then we have dehydrogenation of paraffins. Paraffins, you know that they are, paraffin means having little affinity, so the alkanes are also known as the paraffins. So we have dehydrogenation of the paraffins. Then we have the oxidation of alcohols to form the aldehyde or ketones. Then we have dehydrogenation of amines, hydrazines and their derivatives, and we have oxidation of phenols and anilines to form quinones type of compounds, right? So in this lecture we shall only discuss about the dehydrogenation of the paraffins. right? So paraffins mean having a little affinity. So paraffin is another name for the alkanes. The problem with alkanes is that they are not reactive, so we cannot carry out their reactions with ease. So what we do, that we want to convert this alkane into something that reacts. So easiest way to do this is that we convert these alkanes into alkenes, right? So if we have to convert an alkane into alkene, we have to generate a carbon-carbon double bond, right? So in this lecture we shall see how we can generate a carbon-carbon double bond in an alkane so that it gets converted into alkene. So as previously mentioned, these reactions normally involve input of energy in the form of heat. So you have to provide energy in the form of heat. So reactions are endothermic. So when you give heat in presence of a catalyst, what happens that these two hydrogens are eliminated and we get a carbon-carbon double bond here and the hydrogen gets free. So important thing to note in this reaction are the energetics, right? So enthalpy in this case is positive 80 to positive 120 kilojoule per mole, right? So any reaction to be spontaneous, for any reaction to be favorable, the general thing is that the reaction must have negative enthalpy. So the enthalpy must be negative and this entropy should increase, right? So here in this reaction, the entropy is positive. However, the enthalpy is also positive. The enthalpy should be negative for a reaction to be favorable, right? So we say that this reaction is actually unfavorable with respect to enthalpy because enthalpy is positive, but it has favorable entropy change, right? So since entropy is increasing, so therefore the reaction goes in the forward direction because of entropy. However, the enthalpy is not favoring this reaction, right? So whenever you want to see if the entropy is increasing or entropy is decreasing, just see how many products you are getting from the reactant. So if you are getting lesser number of products from the reactant, then the entropy is decreasing, right? For example, if we have one reactant and we get one product, then entropy is remaining the same. And in this case we are having one reactant and that's converted into two products, right? So number of product is higher, it means entropy is increasing. However, if we had two reactants and that converted into one product, then in that case entropy is decreasing, right? So for a reaction to be favorable, for a reaction to be spontaneous, it is important that entropy should either remain the same or should increase, right? So if a reaction has a decrease in entropy, such reactions are not favorable. Similarly, it is also preferred that enthalpy should be negative. The enthalpy should decrease. In this reaction, although enthalpy is increasing, but the entropy is also increasing. So the increase in entropy is actually the favorable process for this reaction. Now we have two types of dehydrogenation reactions: oxidative dehydrogenation and the non-oxidative dehydrogenation reaction. Right, so we will see about the non-oxidative dehydrogenation reactions first. So these reactions are reversible reactions. When two reactants react to form two products, or a reactant reacts to form two products, and these two products further react to form two products only. So there is no change in number of reactants in these reactions. So since there is no change in number of reactant and product, right? So since there is no change in number of reactant products, so you can predict that the entropy remains the same for these reactions. So since the entropy is remaining same, these reactions are not favored by the entropy. However, these reactions involve exothermic reaction, means the heat is emitted out during these reactions, right? So since the heat is emitted out, it means reaction is exothermic. So enthalpy for these reactions are negative. So these reactions are favored by enthalpy, but they are not favored by entropy. So there is no reducing equivalent involved in this reaction. So no carbon atom goes out of the reaction. So number of carbons in the reactants must be equal to the number of carbons in the product, right? So if you are wondering about what do we mean by the reducing equivalent, so reducing equivalent is any species that accepts the electron donor in a redox reaction, right? Anything that is donating the electrons is called the reducing equivalent or the reducing agent. So a reducing equivalent or a reducing agent can donate either a lone pair, it can donate a hydrogen atom, it can donate a hydride. So hydride is a hydrogen with a negative charge, or it can involve in bond formation with an oxygen, right? So reducing agent can, or reducing equivalent can do any of these things. So in non-oxidation reaction, dehydrogenation reaction, what happens that this reaction is reversible. Second, the number of reactant products remain the same throughout. So there is no number increase or decrease in the number of products. So the reaction is not favored by the entropy factor. So next thing is that we have the oxidation dehydrogenation reaction. So these reactions are favored thermodynamically, right? So these reactions involve increase in entropy. Also, these reactions involve the emission of heat, means they are also exothermic, right? So the enthalpy is negative, which is favorite thing, and the entropy is positive, which is also the desired thing for that. So these reactions are favored thermodynamically. The issue with these reactions is the over-oxidation, means that we don't get only one product, we get a number of products which are oxidized, right? So selectivity is a central problem. For example, maybe you're wanting to generate a carbon-carbon double bond, but instead of generating a carbon-carbon double bond, you also get an oxygen into the molecule, right? So we get a number of side products in these reactions. So the normal undesired secondary side products obtained in such reactions include the polyenes, so means you get more than one double bond inside the molecule. You may get the aromatics, means the system get aromatized, and you may get the oxygenates, means you may get extra oxygen or 2 oxygen into the system as well. So these products are not desired for dehydrogenation reaction, but these products are desired in some other cases as well, right? So these products of polyene, aromatics, and the oxygenates, so they are useful products from other purposes. So it's therefore important that we control these oxidation reactions or the oxidative dehydrogenation reactions for obtaining the practically useful products in reasonable yields. So when we are considering the dehydrogenation of the paraffins, the most commonly used dehydrogenation reaction catalyst industrial level include the mesoporous chromium oxide over alumina, right? So this is chromic oxide over alumina, and you may also use the platinum based catalyst. So normally the industrial alkane dehydrogenations are non-oxidative endothermic processes, right? So they are endothermic processes because we have to give the energy to start the reaction, and the reactions are favored on the basis of their entropy factor, right? So you must know that the industrial dehydrogenation of alkanes are non-oxidative processes. So let's see the mechanism, how the mechanism occurs. So here we have considered a platinum surface. So you're using a platinum as a metal, right? So you know the metal has a high electronic density. What happens that this metal attracts the carbon to itself, and the hydrogen, one of the hydrogen gets detached. The detached hydrogen will get attached to the other platinum, like that. Yeah, right. So in this way we say that we have activated our alkene, right? So what happens next, that there is a sort of double bond formation between the carbon and carbon, you can see here, right? And what happens next is that this molecule loses another hydrogen, right? So this other hydrogen that was previously on this carbon, that has been lost, so the platinum gains another hydrogen here, right? And we get a double bond, right? So in this way the platinum is facilitating in the removal of hydrogen from those two carbons. So by the end we get an alkene, which then gets free from the platinum surface, and these two hydrogens will also get free from the platinum surface. So we get a hydrogen molecule and we get an alkene, right? You can see that from one reactant we are getting two products, so the entropy factor is increasing. So this reaction is an example of non-oxidative dehydrogenation. So instead, if you are using the chromic oxide as a catalyst, this is CrO3 as a catalyst, what happens is chromium, this attracts the carbon to itself, right here. So carbon loses a proton, which is gained by this oxygen, right? Then again we have development of sort of a double bond, and this carbon loses another proton, which gets attached to this chromium right here, and ultimately we get a double bond between carbon and carbon, and the chromium oxide catalyst gains two hydrogen, right? So again we have two molecules from one reactant. So this is example of the non-oxidative process because the entropy is increasing to this factor, right? So whichever the catalyst, the first step is believed to be the activation of carbon-hydrogen bond at the metal center. Right, so let's see it from the oxidative and non-oxidative route purpose. So firstly, the oxidative route, right? So in oxidation, we have increased the number of molecules. We see that here we have a reactant, and this is getting converted into two products, right? So number of products is increasing, so entropy is increasing. This is a reversible process, right? So these reactions, whatever the reaction you take, that always result in formation of the same number of carbons. The number of carbons in this and in this case will remain the same. So there is nothing lost in this reaction, right? Now we'll see about this oxidative route. This is oxidative dehydrogenation. So here we have two reactants and we are getting two products. You see that number of reactant products in this case are remaining the same. So this reaction is not favored in terms of the entropy because the number of molecules are remaining same, but this reaction is favored in terms of thermodynamics because this reaction involves elimination of heat from the system. Right, so since the heat is getting eliminated from the system, the reaction is exothermic. So exothermic reactions are favored. Right, so this reaction is not favored by entropy, but that's favored by enthalpy. Now we have some selective hydrogen route that involves the non-oxidative route. Right, so we are coupling this non-oxidative route and we are trying to make it more selective. So what we do is that this reaction is a reversible reaction. It means that this hydrogen produced in the reaction that adds up to the double bond and converts it back into the alkene. So what we do is that we make use of the Le Chatelier principle, and according to Le Chatelier principle, if you remove one of the products, then the reaction will move in the forward direction. So what we do is that this hydrogen produced in the reaction, we react this hydrogen with oxygen. And when this hydrogen reacts with oxygen, that's being converted into water, and the water is getting eliminated from this reaction medium, right? So in this case, we are removing this hydrogen produced in the reaction and we are shifting this reaction to the forward direction. So since this reaction is reversible, we don't want to make it reversible, right? We just want to convert this alkane into alkene. We don't want this reaction to reverse back. So what we do is that we eliminate this hydrogen by reacting with the oxygen. So this hydrogen gets converted into water and that's eliminated from the system, and we get an alkene here, right? So this is the route of administration. So you can have non-oxidative route as well and the oxidative route as well, but it's non-oxidative route which we are interested in mostly, right? So normally when you are considering about the dehydrogenation of paraffin on the industrial level, so what we do is we carry out the thermal cracking. So cracking is the word given to breaking up a large hydrocarbon into a smaller and more useful hydrocarbons, right? So when you have to break a large hydrocarbon, we have to either give high pressure and high temperature without catalyst, or if you are interested in lower temperature and lower pressure, then you have to make use of a catalyst, right? So when you are carrying out the cracking, there is not a single unique reaction happening in the cracker. What happens is that you are breaking down that hydrocarbon in any manner that's possible. So you can you can break the carbon bonds, you can break the carbon hydrogen bonds, and the breakage can occur at any point. So as a result of the thermal cracking, we get a large number of products, and among these large number of products, a few may have carbon-carbon double bond, right? So thermal cracking is not a useful method for the dehydrogenation of paraffins, because what we are interested in the carbon-carbon double bond. But carbon-carbon double bond is produced in very less amount because we have a large number of side products or side reactions which are also occurring in the thermal cracking. Then in thermal cracking, normally we use high temperatures, right? So you have to use high temperatures in the range of 450 to 750, and we have to make use of pressures about 70 atmosphere to break that large hydrocarbon into small hydrocarbon, right? And we get a mixture of products, and among these mixture of products we may also get some carbon-carbon double bonds as well. So thermal cracking is not involving any ionic intermediate, so we don't get a carbon with a positive charge or carbon with a negative charge. So there is no generation of a cation or anion. Instead, the mechanism is a free radical mechanism, right? So free radical mechanism is a mechanism that involves the breakage of carbon-carbon bond in such a way that each of the carbon ends up with 1 electron each, right? So instead of breaking this carbon-carbon bond, you can break this carbon-hydrogen bond as well, right? So there is no selectivity in that thermal cracking. So you can break this carbon-carbon bond, you can also break the carbon-hydrogen bond as well. But whenever the bond breaks, whether it's the carbon-carbon bond or the carbon-hydrogen bond, whenever it breaks in such a way that each of the two atoms will get 1 electron. So this carbon has 1 electron, this carbon has 1 electron, and the carbon having 1 electron is known as the free radical, right? So in thermal cracking, what we get is the reaction mechanism involves the generation of the free radical. So there is no cation or no anion generation in this method, right? And the reaction is non-selective. It means that we get a number of products that involve the breakage of carbon-carbon bond and also the breakage of carbon-hydrogen bond as well. So when we are looking for the selectivity, we just want to get a carbon-carbon double bond, and we want to get a carbon-carbon double bond at a desired position, right? Then we have to make use of some specialized reagents. For example, we have a specialized reagent which is known as PSCOP, pincer iridium catalyst, right? That's a catalyst. It's shown here, and why we are saying it as PSCOP, because here we have phosphorus. This phosphorus is directly bonded with sulfur. The sulfur is directly bonded with that carbon, and this carbon is again attached with this oxygen. Oxygen is attached with this phosphorus, right? So that's why we are saying it PSCOP, right? So what is this catalyst that these two phosphorus attached? They are being forming coordinate covalent bond with this iridium as a catalyst, right? So the iridium is a central atom, central metal as a catalyst, and why we are saying it's a pincer, because it's just like a pincer. So in Urdu we say pincer as neza. Since the structure is just like a neza, it's just like a pincer, that's why this catalyst is known as PSCOP, pincer iridium catalyst. Right, so catalyst is very selective, but it's very selective only for lower alkanes, right? If the molecular weight is not that much higher. If you have linear alkanes or if you have cyclic alkanes, then this catalyst can carry out the dehydrogenation in a very selective manner. For example, if we have cyclooctane, and with this catalyst we can convert the cyclooctane into cyclooctene. So we have selectively just generated a single carbon-carbon double bond here. Similarly, if we have like this structure and we want to generate a carbon-carbon double bond just here, we are not interested in any other side reactions. So this catalyst is very effective because it can easily generate a carbon-carbon double bond here by using this catalyst here. Right, so this is a selective catalyst, but the problem with such catalysts is that they are highly expensive and they cannot be used for industrial level, right? For industrial level, we are bound to use the method of thermal cracking. So that's all for today's lecture. I hope you have understood it well. Thank you for your patience.